Today I'll be presenting my work on detecting anomalous user behavior in social networks. So I'll jump right into the first. So service abuse is a serious problem in social networks today. There are several black market services available today to manipulate content ratings or popularity of a user. For example, today on Facebook, you can buy, say, 5,000 fans or likes for your Facebook page for as cheap as $20. And we call these users who supply these fake likes as like spammers. Now, the service abuse also has serious economic consequences. Advertising services, this is one of the key sources of revenue for a social platform like Facebook. And these services also seem to be under abuse today. Just to give you an example, recently an advertiser, a startup claimed that 80% of its ad clicks are actually coming from bots. So our goal is to limit this service abuse. And one way to do that is by detecting these misbehaving users or identities in the social networking service. Now, once we detect them, we can suspend the identity, or we can even remove or nullify their actions. Now, first, let's look at some existing approaches to do this. Now, this is a diagram taken from a paper written by Facebook folks, and this is largely representative of most of the existing approaches out there today. The way this works is like this. So today, attackers launch an attack on the social networking service. The operator identifies the attack and launches a new defense to catch that specific attacker strategy. The attacker notices that if the attack is no longer going through, he mutates or adapts to the defense and launches a new attack. This is an endless cycle, where the attacker always has the upper hand. So all these existing approaches, the key problem is that they rely on detecting known patterns of misbehavior. And today, we know that attackers mutate, and they use diverse strategies to abuse these services. For example, they use fake accounts, and they compromise real user accounts, and sometimes we even see real users colluding with each other to boost their reputation. So all these existing approaches are vulnerable against an adaptive attacker. Our idea is to use anomaly detection on user behavior on the social networks. At a high level, we do not try to rely on detecting known patterns of misbehavior. Instead, we build an anomaly classifier that actually learns normal patterns of user behavior, and any behavior that deviates significantly from this normal behavior is considered as anomalous. Our technique is completely unsupervised. This means that we do not require any label data. Instead, the training phase only requires user behavior data for a large random sample of users on Facebook. And the only assumption we make is that most of these users are normal and not misbehaving. And with such an approach, when we are not making any assumptions about the attacker's strategy, we actually have the potential to catch diverse attack strategies. Our key contributions are as follows. We propose an approach to identify anomalous user behavior. Then we apply our anomaly classifier to detect real like spammers on Facebook who use diverse strategies, using Sybil accounts, using compromised accounts, as well as incentivized collusion networks. And finally, we apply our approach to detect click spam on the Facebook advertising platform. And we observe that a significant fraction of clicks look anomalous. Now, first, let's jump into the technique. How do we do this? Now, the key idea is to learn normal patterns of user behavior. Now, for a moment, imagine if every user on Facebook behaved in a very unique way. Or in other words, user behavior data is extremely noisy. Now, an attacker could potentially hide in the noise and try to evade detection. So what we want to see is if there are a few normal patterns of behavior among all users on the social network. Now, why would this work against an attacker? To evade detection, now the attacker would have to behave along these few normal patterns of user behavior. This limits the attacker and constrains and bounds the scale of the attack that the attacker can launch. Let me give you a simple example to illustrate this. Say you're defining users' like activity behavior on Facebook as the distribution of page categories the user likes. So each page on Facebook is associated with a category or a topic. Now, say you're a normal user, you might have limited interest in practice. You might like a few topics or a few categories like football, cricket, and photography. You might like some topics or some categories more than others. Now, if you're an anomalous user or a like spammer, you might have to deliver thousands of likes to your clients, and you might end up liking an arbitrary number of topics here. Now, it should be noted that this is not only about the volume of categories liked, but it's also about the combinations or patterns in them. For example, it's quite unusual for somebody to like, say, bodybuilding as well as dolls, 2-page categories on Facebook. So now that we understand how this would work against the attacker, we still have a hard challenge, which is how do we model user behavior in a social network? Now, user behavior can be high dimensional depending on how you define it. If you're defining it as the number of likes over several page categories, where each page category is a single dimension, you have high dimensional data. Now, this behavior can change over time, and it could also be quite noisy. So how do we do this? This is where a tool like PCA comes in very handy. PCA, or otherwise called as principal component analysis, is a statistical technique to find patterns in high dimensional data. So we use PCA to do anomaly detection. Now I'll try to illustrate how this works with a very simple example where we are trying to define user behavior in 2 dimensions, which is basically the number of likes over 2 page categories, category 1 and category 2. Now let's put some users here. And for a moment, let's assume that a bunch of users are actually normal users, as highlighted here, and there is one anomalous user here. Now, if you look at the normal users, you will notice some pattern there, that most of them have roughly same number of likes for category 1 and category 2. Right? Now, and you will notice that the anomalous user is deviating from this pattern and has significantly deviation from this normal behavior. Now, what we want to do is we want to take a tool like PCA and want to find out automatically which is the anomalous user here. So how do we do that? So PCA takes in this behavior data in 2 dimensions here and proposes alternate dimensions that better explain the spread of the data. So it gives you 2 principal components, or 2 dimensions, and the first principal component will point along the direction of maximum variance in the data. And in this case, it will point along this direction, and you will notice that it immediately captures the normal patterns in the data. And the second principal component, it will be orthogonal to it, and it will point that in the direction that deviates from this normal behavior. We call that as the residual space, and the first one as the normal space. Now, in practice, these 2 spaces can actually include multiple principal components. Now here, to classify whether a user is anomalous or not, what we simply do is we can project that user's behavior onto these 2 alternate dimensions. Now here, if you look at the projection on the normal space as well as the residual space, you can simply see if the projection on the residual space, which captures the deviation from normal behavior, and if you see if it is unusually high, you can mark the user as anomalous. Now, before we jump into actually using this technique to catch anomalous users on Facebook, let's just try to see our main requirement of whether there are a few normal patterns of behavior in Facebook. Now, we will do that by actually looking at Facebook's like activity. We will define Facebook's like activity user behavior as the same one I used before, which is the number of likes over many page categories. We will use over 200 page categories as defined by Facebook. And we will apply PCA to this behavioral data. Now, each principal component will correspond to some behavioral pattern. And we can try to see if there are a few dominant patterns of behavior by looking at the fraction of the variance each principal component captures. Now, this plot answers that question. So here on the x-axis, you have principal components ordered based on the fraction of variance it captures. On the y-axis, you have the fraction of the total variance by each component. Let me enlarge this plot. So what you will notice here is that the top 5 principal components in this case actually account for more than 85% of the data variance. And almost all the remaining components capture a negligible portion of the variance. So what this means is there are like 5 normal patterns of behavior that you could use to capture normal behavior in Facebook's like activity in this case. Now we notice this not only in Facebook, but also in other social networks like Twitter as well as Yelp. Now that we understand our technique, let's try to apply it to real data and see how it performs. Now, the first thing we need to do is to build the classifier, we need to train and understand these normal patterns of behavior. To do that, we trained on the behavioral data, or in this case, the like activity information for a large random sample of users on Facebook. To test how our classifier performs, we got ground truth information about like spam on Facebook. Now, getting ground truth information is quite hard, and there are a lot of details that I'm skipping here, and you can look at in the paper to find out. So we found out there were 3 types of like spammers that we can actually test on. One type of like spammers, they were mostly fake accounts, that the ones that we got from the black market. Then there were accounts which were compromised, accounts of real users, and they were engaging in like spam. And then there were some real users colluding with each other to boost the like count on their pages. Finally, we also included some normal users, and these were users who were friends of our co-authors, as well as users who were part of trustworthy Facebook groups. Now let's look at some of the detection results. Here, what we find is that our anomaly classifier is able to flag most of the anomalous activity by these 3 types of misbehaving users. So this actually performs quite well. Now, when we tested this on the normal users, we flag roughly 3.3% of these normal users, which can be considered as the false positives here. Now, let's jump into the second application of our technique. Now that we can catch like spam, let's look at how can we apply this anomaly classifier to detect click fraud on the Facebook ad platform. I'll jump into a bit of motivation here, but so you've already heard about click fraud and all from the previous talk, but the main problem here is that advertisers lose money on spam clicks. And because if this happens, they might lose confidence in the advertising platform, and this affects the sustainability of the social networking service, in this case, Facebook. Just to get a preliminary understanding of the level of click spam, we did a very simple experiment. We set up a real ad targeting users in the US to do a particular survey, a simple user survey. And we also set up what we call as a bluff ad, which is basically an ad with nonsensical content. In this case, it was almost empty. There's nothing in here. So what you would expect is that the users would actually click on the real ad, and you would probably not get any clicks for the bluff ad. But we had got very unexpected results. We got near identical performance for both the real and the bluff ad. So we got almost similar number of clicks and similar levels of activity on the landing page. So we wanted to investigate this further. So now we have this nice tool of anomaly classifier that we can actually try to investigate whether these users who clicked on these ads have anomalous behavior. So how do we do this? First, we create an ad to get likes to a Facebook page under our control. And then what Facebook does is it will target users who are more likely to like the ad, or in this case, click the ad, and forward them to our page. Then we apply our anomaly classifier to the like activity behavior of these users who clicked like on the ad. We set up 10 such ad campaigns targeting over 7 countries. We got some very surprising results. Almost 67% of the clicks on our ads looked anomalous. 8 out of 10 campaigns had a majority of their clicks that looked anomalous. Even the countries in the US and UK campaigns had more than 39% of their clicks marked as anomalous. There are lots of details I'm again skipping here, but they're all in the paper. So far we have identified like spammers, and we also applied it to find click spam. Now while doing this work, we found out that Facebook has its own defense system deployed called copycat to catch like spammers. So we wanted to validate our findings with Facebook. So we carried out this whole set of experiments over the year in 2013, and what we did was we took another snapshot of all the users we flagged and their activity that we flagged, again, very recently in June 2014. And we can make 3 interesting observations. First, Facebook hardly suspended or removed any of the users we flagged. Instead, what they seem to be actually doing is cracking down on their misbehavior or their activities. So one interesting finding was that more than 85% of all the likes by the ad users that we flagged, or the click spam that we've identified, were removed by Facebook. So this confirms our click spam findings, because there we actually did not have ground truth information. But Facebook system still seems to be lagging behind on catching all the misbehavior. So most of the majority of the likes from the black market users or the fake users still exist on Facebook even after 10 months. To conclude my talk, I started off by saying that service abuse is a huge problem in social networks today, and attackers are smart. They use diverse strategies and try to adapt. So we propose an unsupervised anomaly detection approach to catch misbehaving users. And we find that principal component analysis is a nice tool to model user behavior and find deviant behavior from normal. We evaluate our technique on extensive ground truth data of real like spammers on Facebook. And we also apply our approach to detect click spam on Facebook and find that a surprisingly large fraction of clicks look anomalous. Thank you. Happy to take questions.
Okay, I have a quick question here. So as far as I know, Facebook doesn't syndicate ads from third-party publishers, right?
Right.
So what is the motivation of these like sellers to like
That's a good question.
pages when you're not paying them to like them?
Right, that's a good question. I wish I knew the answer. So this is something that we do not know either. And we have some theories on what could possibly be happening. One thing is that some advertisers are trying to kill somebody else's budget, advertising budget, the attacker. So that's one theory. The other possibility is that we analyzed these users we flagged, and we looked at their activities, and we tried to see how well they match with the ground truth like spammers we had, the black market compromise users and so on. We found out that the majority of them actually match the black market user data. So one theory is that the black market users are trying to use this click spam or this as cover traffic, and they're randomly clicking on ads on the page to hide behind the noise. That could be one.
Yeah, early on you pointed out the attack, detect, respond cycle in which defenders are always going to be behind. The domain that you're working in seems to be fairly constrained in the number of patterns and things. Do you think that your work could generalize to other places where the attack, defend, response cycle is in play?
Well, I believe so, yes. So this technique is quite general. PCA is a well-known statistical technique. And as long as you can model normal patterns of behavior, if you're looking at users in the case of social networks, you can apply it across systems. Yes.
Thank you.
Hi. You used the example of users liking different categories. It seemed a bit odd together. Like I think you mentioned bodybuilding and dolls. Have you considered the possibility that adversaries might specialize their compromised or fake accounts in order to sort of appear more normal, as well as the other patterns that you had mentioned that you use for the top 5 principal components?
Right. So that's a good question. So this is exactly why we actually tested on a wide, diverse set of attackers. So we actually tested it on compromised users. And you would actually think that, oh, it would be hard to catch compromised users. Yes, it would be hard. But once the attacker compromises the account, their behavior actually deviates from normal. That's what we found. And this enables us to catch a whole lot of this misbehavior.
Yeah, but it deviates from normal because they don't know about the existence of your system. I'm saying if you equipped adversaries with knowledge that your system exists, is it possible that for them to thwart it using specific techniques?
Okay. So now you're asking, so this is a question where, in some sense, there's a training phase of this whole classifier where you're trying to learn normal patterns, right? Now, if the attacker manages to compromise the training phase, then yes, it is possible. In theory, such attacks are possible, but in practice, I would think it's pretty hard because the attacker would have to compromise a whole bunch of accounts on Facebook. So today, Facebook claims that around 3% of accounts are suspicious on Facebook. So, and data is already tested on that much set of misbehavior. So that's like 13 million accounts if you consider 1 billion population. So you'd have to compromise a lot of accounts to manipulate these principal components and affect the classifier. Yeah. And there's a talk right after mine which talks about adversarial scenario in more detail. So.
Algus Regis, Google. Related to that question, I guess another approach to attacking this would be a low temperature attack. So instead of, you basically minimize the amount of anomaly you have, what is the threshold of anomaly? How anomalous does an account have to be before you start flagging it?
Right. So that depends on the operator in terms of how much false positive the operator wants to tolerate, or look at the verification resources the operator has in place. So it's tunable parameter, of course, and you can trade false positives for false negatives.